Good morning, students. I hope you all are doing very good. I'm sending this video to have a little bit of explanation on the very first note that I have sent to you. That is the surface integrals. You refer your note for explanation. Okay, let me read. Let us first consider the case of a surface S of the form z equal to phi of x and y. This is the first way of defining a surface. Remember, this is a surface in R3. Here, Z is fully expressed in terms of x and y. It means that for any value of x and y, the value of Z is fixed. Okay, where x and y ranges over some domain D of the xy plane. Remember, this D is a domain for this function, and it is in the xy plane. Now, let h be any function of x, y, z which is continuous in some domain containing the given surface. Remember, this is a function we have to integrate, and it is a function in R3. It has three variables, x, y, and z, and it also should be continuous in its domain, and that domain of this function h should contain the given surface. It should contain this surface S. This surface S is in the form of z equal to phi xy. Let's see, denote the boundary of D and draw the boundary curve of the surface. Let me explain you with an example. Suppose if we have a surface, a unit sphere. Let me draw a unit sphere. Okay. Suppose this is the x-axis, the z-axis. Let me draw the y-axis. This is the y-axis, and this is the origin. This is the radius of the sphere. Since I'm talking about a unit sphere, so this radius is equal to 1. Now, what will be this equation? A unit sphere, remember, it is x square plus y square plus z square equal to 1 square, which 1 is the radius. We're talking about a unit sphere at the origin O. Now, if I want to express z in terms of x and y, then it will be 1 minus x square minus y square, then the square root positive and the negative. The upper one will have to take the positive sign, and the lower one will have to take the negative sign. So this function phi is this one. Okay, so here z is fully expressed in terms of x and y. What will be the domain of x and y? if we project the sphere on the xy plane, we will get, suppose this is an xy plane, we'll get a unit circle or a disk. It contains the whole part of the circle, so we will call it a disk. So what is our S? Our S is a unit sphere, and our D, this D, which is the domain in the xy plane, will be this disk, a unit disk in the xy plane. Okay, let's forget about H for some time. Now C denotes the boundary of D. D, remember, is in the xy plane. The boundary will be a unit circle. D is the whole disk, the whole of this disk, and the boundary C, the boundary of this D, which is the disk, will be this unit circle, will be this unit circle. And rho is the boundary curve of the surface. Remember that the orientation of rho and the orientation of the boundary curve, that is rho, and the boundary and the orientation of C, which is the boundary of D, should be the same. Then what do we have? Then integration over a surface S. In our example, it is a unit sphere. Integration over S of the function h x, y, z dx dy is equal to this one. Okay, what do we do here? S, which is the sphere, okay, z, in this case we express it in terms of x and y. So we also have to change the portion of integration from S, which is the unit sphere, to the domain of x and y in the xy plane. That is in our example, it will be our unit disk. So we have this one. Now in the next page, we have another way of expressing a surface in R3 or in three-dimensional space. Here we parameterize for x, y, and z. We express x fully in terms of u and v. Similarly, y, we fully express it in terms of u and v. Z is also fully expressed in terms of u and v, where u and v belongs to the domain D1 of the UV plane. Then what do we have? Then for this function, for this integration, over D of the function h, then we have integration over D1. Remember, D1 is the domain for u and v. Then h of the function h in the variables x, y, and phi which is set. And then we have to find out the Jacobian del xy del uv. Then we integrate it in u and v. This one is what? It is a previous integration. We can, if we relate these two integrations, it is from this definition in the previous page. Therefore, what do we have? This is equal to this, then we have equal to this integration. So integration over s of the function h in the variable x, y, and z dx dy is equal to the integration over d1 of the function h in the variable x, y, and z, then the Jacobian del xy del uv du dv. Why we are coming from the first from this sphere, from this unit sphere, we express z in terms of x and y to make it simpler. Now there are some functions that we still have some problem or still difficult to find out. Then we change it to the parameterization form, that is x in terms of u and v, y in terms of u and v, and z is equal in terms of u and v. So from S we're coming to the domain D. D is in the xy plane. Then we're coming to D1. D1 which is for u and v. D is for x and y in the xy plane, uv plane. Suppose if we want to parameterize this disk and express it in terms of u and v, then we have to find out how do we express for x and y. Now if we express for a disk, remember for a disk, if we express x equal to r cos theta and y equal to r sin theta, and here we suppose this r is my u, this r is our u, and this theta is our v. So from x and y we're changing it to r and theta. But since we're talking about a unit disk, this r is equal to 1. R is equal to 1. X equal to cos theta and y equal to sin theta. And what will be the 1? For r will have to vary from 0 to 1. So r will have to vary from 0 to 1. And theta is the angle. It will vary from 0 angle, 0 degree, to pi. Okay, for theta, here is 0, here is pi by 2, then pi, 3 pi by 2, then we're coming to 2 pi. Then we have this equation. Now, okay, I have a look here. Here it is with respect to x and y. It means dx dy. You change it to du dv. Similarly, okay, let me write. If we want to project the sphere, if we want to project the surface in the xy plane, we have this. If we have dx dy, then we have the domain D in the xy plane, and for z we express it in terms of x and y, dx dy. If we parameterize for x and y, then we have d1 but remember, x, y, and z we should express in terms of u and v. Similarly, if it is dy dz, let me not write h, but let me use a different function f. This d is in the xy plane. Okay, let me write e for in the yz plane, and let the function be expressed by this, and you have dy dz. But here we have to write the Jacobian del xy del u v, right? Then here will be d1, since we want to write in terms of du dv. Then the function f x y z del yz del u v, since we're changing from yz to u v. And x, y, and z should be in terms of u and v. Similarly, if it is dx dz, but let me write with a different function, g x y z. Let me not write e, since this e is in the yz plane. Let me write f. This f will be in the xz plane. Sorry, here this should be set. This should be set. Here we express x in terms of y and z. So let me write psi here. This psi should be in terms of y and z. And here we express y in terms of x and z. Let me write a different function, say beta. This beta is for y. It depends on x and z. dx dz equal to, here it will be d1, since I want in u and v. Then g of x, y, z. This time x, y, and z I should write in terms of u and v. Then the Jacobian, I change it from xz to uv, del uv. If you add all the three together, if you have this plus this plus this, then you either have this plus this plus this, or you will have this one plus this one and this one. Now let's do one problem. Let's evaluate the integration I. We integrate it over S, over a surface S, x dy dz, dz dx, plus xz square dx dy, where S is the outer side of the part of the sphere x square plus y square plus z square equal to 1 in the first octant. Let me draw S. If this is the x-axis, this is the z-axis, and this is the y-axis. So we're going to have only this part of the sphere in the first octant. Okay, we leave 8 parts of the sphere. At the back of this, here we have, on the upper side of this we have 2, then below this xy plane we have 4 octants. But in our problem we have to integrate over this outer part of the sphere, which is only in the first octant. Here we have all dy dz, then is set dx and dx dy. Here it is xz square, here it is 1, and here we have x. Okay, and we integrate it over S. If I separate them, I separate the integration sign, we have S plus s plus integration over s. We'll have to find out, we'll have to evaluate them separately. So let me name this as I1, this as I2, and this as I3. Okay. In I1, we have y set. In I1, we have y set. So if we come from S, and if we project S on the y set plane, y set plane, y set plane, we are going to get a quarter circle of radius 1. Similarly, for solving I2, then we project this surface S on the set x plane. This is x axis, this is z axis. If we project S on the xz plane, then we're going to get a quarter circle of radius 1. Similarly, here if we evaluate I3, we have to project S on the xy plane. Suppose this is the x-axis, this is the y-axis, the origin O. Then we'll get a quarter circle of radius 1. For I1, we have y and z. But in the function, we have x. So this x, we will have to express it in terms of y and z. Using the equation x squared plus y squared plus z squared, we can express x in terms of y and z. So it will be 1 minus y squared minus z squared. We should take the positive sign, as we're going to take the octant to be on the opposite of z. So this is my equation. X should be in terms of y and z. Then dy, dz. And the portion for integration, let's write it d1. This d1 is the domain in the yz plane. To integrate this one, we'll parameterize for y and z. So if we write y equal to r cos theta and z equal to r sin theta, since it is this quarter circle, r will have to vary from 0 to 1. The radius r will have to vary from 0 to 1. And theta, which is the angle, will have to vary from 0 to pi by 2. Therefore, from your note, since we are changing y and z to r and theta, we have to find out the Jacobian del yz del r theta. After finding out the Jacobian, then you have the Jacobian equal to r. Then your I1 is equal to, substitute these values of y and z, you are going to have this. Then modulus of the Jacobian dr and d theta. After evaluation, you'll get equal to pi by 6. Similarly, you will have to do the same thing for I2. You project S on the xz plane and you will get a quarter circle, and you parameterize for x and z. You'll have the same thing. You find out the Jacobian since you're changing from xz to r theta, so you'll get the Jacobian equal to r. Then you evaluate for I2. Theta is varying from 0 to pi by 2 and r is varying from 0 to 1. Then you'll have pi by 4. Similarly for I3, you're changing the variable. So you project the surface S on the xy plane and you are going to have a quarter circle. To make it simpler, you parameterize for x and y. You change the variables x and y to the variables r and theta. Since you're changing the variables, so you have to find out the Jacobian del xy del r theta, and you're going to get it r. You substitute the values in the given integral, then you'll get the value of I3. Remember, in I3, theta is varying from 0 to pi by 2, then your r is varying from 0 to 1, since all of them are quarter circles. Then I3 is equal to 2 by 15. Therefore, our integral I is equal to I1 plus I2 plus I3. You add all these three terms together and you will get it 5 pi by 12 plus 2 by 15. Here you have the next example, and I want you to try this example. You refer the last example if you have any problem. Thank you.